Okay, so in the last video we saw the notions of connectivity and edge connectivity. So today we are going to link them, and we also throw in the mix the minimum degree of the graph in this proposition. So this one says that if G is a graph that is non-trivial, then its connectivity is less than or equal to its edge connectivity, which is less than or equal to its minimum degree. So let's see how we can prove this. Let us first handle the case where G is disconnected. G is given to be non-trivial, fine, but still G can be disconnected. If G is disconnected, then we already know that the connectivity of G and also its edge connectivity are both equal to 0. So in this case, the given inequalities are trivially true. That is because both of these quantities are 0, and this, the minimum degree of G, is by definition a non-negative integer, so the inequalities in this case are trivially true. Now assume that G is connected. So now G is not only non-trivial, but it is connected also. Okay. Now first of all, the author proves this second inequality in just one line, but let us first see what he has to say, and then we will try to understand it. The inequality less than or equal to delta of G is true because the removal of all the edges incident with a fixed vertex in G separates G. Okay. Now what does this mean? Let's see. Suppose this is our graph G. What this line says is that if we remove all the edges incident with a given fixed vertex in G, nothing else has been said about what sort of vertex we have to choose. It can be any vertex, but once you fix it, it stays fixed. So after the removal, G gets separated or G becomes disconnected. Why? Suppose you have any vertex V in G. You have chosen some vertex V in G. Now because G is non-trivial, so this cannot be the only vertex in G. There should be at least another vertex. And because according to our assumption G is now connected, those two vertices will have a will have a path between them in G. So in any case there will be some neighbors of this V. Some neighbors. At least one neighbor must be there because of G being non-trivial and connected. Now here we are saying that if we remove these edges incident with this fixed vertex V, then this disconnects G, which we can see is true because after that removal G will have two components. Keep in mind that G according to our assumption is connected. So after the removal G will have exactly two components. One of the components will contain only this vertex V and the other component will have the other vertices, the rest of G, G minus V. So that disconnects G. Okay. Now to have this disconnected subgraph of G, we had to remove a number of edges from G. Fine. But lambda of G, the edge connectivity of G, is by definition the least possible number of edges in G that need to be removed in order to disconnect G. So naturally this lambda of G will be less than or equal to this number of edges. Okay. Now this V was arbitrarily chosen to be any vertex in the graph. So in search for a minimum, that is in order to have these edges, as few edges as possible, we would naturally choose a vertex V that has minimum possible degree, because there also such a removal will give us a disconnected graph. So lambda of G must be less than or equal to the minimum degree of the graph, which by definition is the minimum degree of the minimum among all the degrees of the vertices of the graph. But this lambda of G obviously can never exceed delta of G, because this many removal of this many edges is already giving us a disconnected graph. So the minimum number of edges that need to be removed in order to disconnect the graph should not be greater than this. It should be less than or equal to this. That's why we are getting this inequality. Now if you are thinking of when you will have a strict inequality and when you can have equality, for that you can take some examples. For instance, you can consider this graph, say. Say this is our G. It's a non-trivial graph. It has more than one vertex. It's also non-empty and it is connected also. Now here if we label the vertices with their degrees, then these vertices get the labels 2 and these two vertices get the labels 3. So here minimum degree is 2. However, the edge connectivity is 1 because of the presence of this bridge. If you remove just this single edge, then the graph becomes disconnected. So that's why in this case you are having a strict inequality. As opposed to this, if you modify this graph itself a little bit, like this, say. Then for this, say this is our G1 and this is the G2. In this case, you will see that H connectivity is no longer 1 because this is no longer a bridge. It has now become a part of, say, this cycle. So its removal does not disconnect the graph. In this case, the H connectivity is 2 and the minimum degree is of course also 2 because we do have a vertex of degree 2. Why is H connectivity 2? That is because removal of these two edges, which corresponds to an operation like this. Say here you have chosen V, that V here is this vertex, or you can choose this vertex also. There are two such choices. After choosing that, fixing that vertex, if you remove these two edges, then the graph becomes disconnected. So H connectivity should be less than or equal to 2. However, it cannot be 1 because there is no bridge. At the same time, it cannot be 0 because the graph itself is connected. So that's why it must be equal to 2. Okay, so that gives us the second inequality. Now we see how to prove the first one. To prove the inequality kappa of G less than or equal to lambda of G, we choose a minimal subset F of the H set of G such that G minus F is disconnected. So that means this F, for example, is like, for this graph, the set of these two edges. Okay, so that their removal disconnects the graph and F is minimal in the sense that F has as few edges as possible, maintaining this condition. Now there are two cases. So to prove this inequality, that means what? Okay, the minimal nature of F and this condition tells us what? It tells us that the number of edges in F is actually nothing but the H connectivity of G. Naturally, that is the definition of the H connectivity. So that means we have to prove that the connectivity of G is less than or equal to this number. That's enough. So we now have to prove that the connectivity of G is less than or equal to this number. Now two cases will arise. First, suppose that G has a vertex V that is not incident with any edge in F. G may or may not have such a vertex. We have to consider both the cases. This is the case where there is a vertex in G that is not incident with any edge in F. Okay. Let C be the component of G minus F containing this vertex V. So the situation now is like this. Should I draw the figure now itself? You can understand what we have written here. Since F is a set of edges whose removal disconnects whose removal disconnects G, so we started with a connected graph G. So G minus F will have at least two components. It may have more than two components, but this vertex V will lie in one of them, one of the islands after removal of F. That is because removal of F is removal of edges. No vertex of G has been removed. So V will remain after that removal also. So V will belong to some component. Let that component be C. Then, now after this we are going to write two lines and then we will draw the figure. Then the vertices of C that are incident with an edge mid ink. That are incident with an edge in F. Separate V from G minus C. Okay, let's draw the one figure to understand this line. So this is our C, the component that contains V. So suppose the vertex V is here somewhere in C, and the rest of G is here. In this part there may be more than one component. Okay, so this is not necessarily a single component in G minus F. So this is G minus C, and in fact in G minus C we also have the set of edges F. I mean the edges of F are there in G minus C. G minus C is obtained by removing the component C, all the vertices and all the edges that are incident with the vertices of C. After removing them we are getting G minus C. In G minus C we do have F. Okay, now to sort of show that if removal of F gives us a disconnected graph from the original graph G, we can somewhat vaguely try to imagine F like this. Okay, there are some edges that are in a sense connecting C with the rest of G, that is G minus C. So this is F. In this vague region we have F. Now the nature of this vertex V is such that V is not incident with any edge whatsoever we have in F. But since F is connecting C to the rest of G minus C, there will be vertices in C that are incident with edges in F. Say these are some edges from F, and these are those vertices of C that are incident with some edge in F. A single vertex may be incident with more than one edge in F. That possibility is also there, but at least one. We are considering only those vertices of C such that each one of them is incident with at least one edge from F. Okay. Now what we are saying? We are saying that if we remove these chosen vertices, now we are talking about removing the vertices, not the edges in F. If we remove these vertices, then after that removal, phi will be separated from G minus C. How? Suppose that is not the case. We have to draw it once more here for the sake of clarity. Say we have these vertices here somehow. This is our F. This is C, and this is our G minus C. It should be understood, again I am repeating, that F is a part of G minus C. Although we are sort of showing this to be G minus C, but F is a part of G minus C, that is understood. Now we are claiming that removal of these vertices separates V from from G minus C, and suppose that is not true. That means what? It means that even after removing these vertices, there should be a way of going from V to the part G minus C. So there should be a path like this. That is going from V to G minus C. And that path actually should pass through F. In other words, that path should contain at least one edge from F. Why? Because if that path entirely evades F, it does not take any edge from F, then removal of F does not disconnect G, because this connection stays intact, no? If that is the case. So that's why this path should pass through F, in the sense that it should contain at least one edge from F. But if that is the case, then in this path, going from V, we will encounter some vertex which is incident with one edge in F. Okay, but then that vertex should have been in this collection, in this class of vertices whose removal we are talking about. So that's why, and that is a contradiction, because we are treating this path to be a path which is there, which survives after removing these vertices. So that sort of vertex should not be there. So that's why no such connection survives actually after removing this sort of vertices. And that is why it is justified to say that the vertices of C that are incident with an edge in F separate V from G minus C. That is, their removal separates V from G minus C. Okay. Now the next line is this: since no edge in F has both its ends in C, and the reason is this: by the minimality of F. There are at most this many such vertices in C, of course, giving connectivity of G less than or equal to the cardinality of F as desired. Now, what is this again? Okay, so now the situation is this. Our aim is what? Our aim now is to somehow estimate the connectivity of G. The connectivity of G is by definition the minimum number of vertices that need to be removed from the graph in order to make it disconnected. We have already obtained a class of such vertices whose removal disconnects V from G minus C. That means it disconnects the graph. So by the very definition of connectivity of G and its minimality, this should be less than or equal to the number of such vertices. So that means we can estimate this kappa of G if we can estimate the number of vertices that we have here in terms of what? In terms of the cardinality of f. Now here what we are saying, since no edge in f has both its ends in C, there are at most this many such vertices, this type of vertices whose removal disconnects V from G minus C. Let us first try to understand this part. Why is there no edge in F, both of whose ends lie in C? If we have such an edge, what goes wrong? So this is our F, and this of course is G minus C, this is F, this is C. Among the many edges in F, suppose there is an edge, both of whose ends lie in C, that is, both the ends of this edge are vertices in the component C. Then what goes wrong? Since removal of F disconnects G minus F is disconnected, that's how we have chosen F, and F is a minimal subset. So once we perform that operation, this edge will not be there along with the other edges in F. So C becomes a component, an island in itself, and the rest of the graph G minus C, actually G minus F, it has the other components. However, at that stage, because these two vertices are lying in the component C, so by the definition of a component, the component itself is a connected subgraph. So there should be a path in this component that connects these two vertices. Okay. And that path naturally will not contain the edge that has been removed. So that means this particular edge, both of whose ends are in C, that edge is part of a cycle like this. Now under this situation, we want to claim that actually if one removes this particular edge from F, then also one gets such a disconnecting set of edges, which is smaller than the original F, and that would contradict the minimality of F. Now the question is how? Say, so the original F is a set of edges whose removal disconnects the graph. Now because this edge lies in a cycle, so its removal or its non-removal does not affect anything, because the connection that we have between these two vertices, which is here, that is not being affected. Whether if this edge is there or not, it does not matter. It loses its usefulness as an element of F. So that's why if we remove this edge from F, we are still getting a set of edges whose removal disconnects the original graph, and that contradicts the minimality of F. So that's why I hope this part is clear to us. Because this edge now has become a part of this cycle, so it can be removed from F, and that resulting subset with one element less still disconnects the graph, because originally the removal of all the edges from F was disconnecting the graph, But we have now found that this edge actually plays no role in that disconnection. So that's why f can be made smaller. So that contradicts the minimality of f, and that is why no edge in f has both its ends in C by the minimality of f. Fine. But now, taking everything into account, how are we saying that there are at most this many such vertices? Such vertices means this type of vertices whose removal disconnects V from G minus C. How? Let us see. So we now, in reality, we don't have this type of connection which evades F, the set F totally, and such a vertex is actually part of this class of vertices from C, whose removal disconnects V from G minus C. Suppose the number of such vertices is n. Okay. Now we want to say that n is less than or equal to the number of edges in F. How? Note that the way we have chosen these vertices, each vertex corresponds to an edge in F with which it is incident. Now, can two different vertices be incident with the same edge? No, because that happens only when this is the case. Here two such vertices are there in C which are incident with the same edge. If that happens, then those two vertices must be the ends of that edge. However, that we have seen is not true. So different vertices correspond to different edges from F. We may have a vertex like this which corresponds to more than one, which is incident with more than one edge from F. That is possible, but two vertices cannot be incident with the same edge in F. That's why the number n, you can clearly see, will be less than or equal to the number of edges in F. We may have some edge in F which is not incident with any vertex from from C. That possibility is also there. So which will only make cardinality of F even more. But F can never be less than n, because then we will run out of edges. That is not the case, because that's how we are choosing these vertices. So that's why n is less than or equal to F, cardinality of F, and removal of these n vertices is disconnecting the graph. So the minimum possible number of vertices whose removal disconnects the graph, which by definition is the connectivity, must itself be less than or equal to n. So that's how we are getting this. Okay, and all these things have been possible under the assumption that there is a vertex V in the graph which is not incident with any edge in F. By the way, how is that assumption being used here? Where are we needing that thing? That is because, you see, phi is not among these vertices that are being removed. So after removal of these vertices, you can see that we do not lose everything from the component C. at least V stays there. So that makes the graph disconnected. Because if there is no way of saying that V is not one of these vertices, then who knows, maybe V also is one of these vertices. So then if you remove these vertices, and if things are so bad that every vertex in C turns out to be incident with some edge in F, then all of them will be removed. But then that does not disconnect the graph. After removing all these things, whatever you have here, we don't know whether it is disconnected or connected. But now, because of the presence of V, after removing these vertices, we know for sure that the resulting subgraph is disconnected. So that's why we have been able to proceed like this. Now comes the second case where no such V is there. Okay, so we can clean this part. Suppose now that every vertex of C, or in fact not just C, every vertex in the graph is incident, because C comes after choosing V. C is the component where we have V in the graph G minus F. That's how we have chosen C, right? So now there is no vertex in the graph that is not incident with any edge in F. Or in other words, every vertex in G is incident with at least one edge in F. So now there is no special vertex. We are going to arbitrarily choose any vertex. Let phi be any vertex in G, and let C be the component of G minus F, I think it is. Yes, again component of, because G minus F continues to be disconnected, so it will have components, at least two components. In one component there will be this vertex V containing V. Then the neighbors W of V in C satisfying or neighbors of W in V, W of V in C with the edge VW not belonging to F lie in C and are incident with distinct edges in F. giving. So here also we are saying many things at once. We will now try to understand them. Okay, now here what do we have here? Again we have C, again we have F, and again we have G minus C. F is a part of G minus C. Okay, now say this is V, and so what we are saying, the neighbors W of V in C, of course, W in C, with VW not belonging to F. Lie in C. Clearly they must lie in C and are incident with distinct edges in F. So these are say edges whose one end we are showing in C and the other end we are not showing. That means these are edges in F. There may be more than one such W, say this one, such that W prime also belongs to C and the edge VW prime is not in F. This W prime will also be incident with some edge in F, and because every vertex in the graph is incident with something from F, so V itself is also incident with some edge in F. And now what we are saying, with distinct, okay, so these W's are incident with distinct edges in F. How? Suppose this W and this W prime are incident with the same edge in F. Then that edge in F should have one end W and the other end W prime, and we will have a situation like this, so which will again you can see contradict the minimality of F, because removal of that edge from F will give us a smaller F whose removal still disconnects the graph. So that's why these edges which are incident with different such vertices from C are different. Okay, they are distinct edges. Also you can see that this edge that is incident with V and it is coming from F, that is also not one of these edges. Why? Because in the case where these two ends are the same, even in that case these two edges cannot be the same edge, because then W and V should coincide, but then W, in that case W will be V, and V is not a neighbor of itself. So that's why all these edges are distinct. Okay, we don't however need to consider this edge at all. Do we need to consider this edge? I mean to conclude. Now we need, of course, because here we will be saying something about the degree of V. So the number of edges incident with V is the degree of V. Yes, but in any case these edges are all distinct. Okay. So does that not tell us that the degree of V should be less than or equal to this? Why? Because the degree of V corresponds to such the number of, it is equal to the number of such edges which are incident with V. okay, and each such edge corresponds to an edge from F that is distinct, I mean that is unique. So we should have at least as many edges in F as we have edges that are incident with V. In other words, this should be less than or equal to this. Okay. Now how can we use this inequality? I hope you can understand, because after going through the argument, if one now looks at this diagram, it shows almost nothing. I mean, it's a mess. But we went through the argument, and in the course of that process, the diagram was meaningful. Now it has become a mess, as the neighbors of the set of neighbors of the vertex V in G separates V from the other vertices in G. From all the other vertices in G. This yields again our desired inequality, but there is one more thing: unless there is no such other vertex, unless there are no other vertices. That is, if this is equal to the vertex theta G itself. So let us now try to understand this part. Now there is no need to look at this diagram. We have this, we used this diagram to obtain this inequality. Now we will start from here. We will use just this. Fine. So now the situation is this: you have the graph G, and there is a vertex V, which is actually any vertex. It has neighbors Now if we remove, now we are not talking about removing the edges, we are not talking about the removing of the vertices which are neighbors of V. This will, the removal of all these neighbors of V will disconnect the graph G. That's what we are saying as this separates V from all the other vertices in G, whatever else we have in G. So that's why this inequality yields this, because if you have some other vertex in G that is not one of these neighbors. Then after removing these neighbors, the connection between V and that vertex has been severed. So that will make G disconnected. And because removing this many vertices disconnects G in that case, so the minimum number of vertices that need to be removed in order to disconnect G, or in other words the connectivity of G, is less than or equal to this number, which is the number of such neighbors in neighbors of V. And that in turn implies that this is less than or equal to the cardinality of F. But removing these neighbors will not disconnect G if G has nothing else, if this is all what G has. That is, if G looks like this, there may be only one such vertex, but there is at least one, because we know that G is given to be a non-trivial graph. We started like that. Okay, if this itself is G, then removing these neighbors does not disconnect G, because once you remove them, you have a single vertex, which is a connected graph. So that is the neighbors of V and V give us all the vertices of G. So if this is not the case, then we are done. But if this is the case, then of course we are not done. But since V was chosen to be any vertex in G, so we are not done if this happens for every vertex in G. And that is a special case. Since V was arbitrarily, have I written the spelling correctly? Arbitrarily, okay. Arbitrarily chosen we only have to now look at the case where G is a complete graph. Naturally, because that is the only case if this is true for all the vertices of G, because then whatever vertex you choose, the other vertices, whatever else is there in G, all of them should be neighbors of that vertex. In other words, every vertex is adjacent to every other vertex. That's why G is complete. In this case, both the connectivity of G and the vertex connectivity are equal to the order of G minus 1. So in this case also the inequality is true, and in fact it's an equality, and this completes the proof of this result. It is somewhat long, and it's not long actually. If we try to understand each and every line properly, then it becomes somewhat long. But now we have this result. So let us see what this result says. Let's see about that a little. The problem with this type of arguments is that if we are not careful, since we are saying something, making some statements about a class of graphs, which most often is an infinite class. There are infinitely many graphs about which we are saying something general. So we should go very carefully with the argument, and taking specific examples may mislead us, because there may be something in our specific example that does not capture the full generality of the situation. We may inadvertently end up using some particularly easy thing from that special example that we have taken to understand the situation, which may not be there in the other examples from that class. So that's why we consider general diagrams like this, in spite of the fact that taking a specific example is always more illuminating. But then you will have to consider all the special cases from that class of graph about which we are saying something, and that is not possible because there may be infinitely many. Anyway, by proposition 142, high connectivity requires high minimum degree. Naturally, because your connectivity is less than or equal to H connectivity, which is less than or equal to the minimum degree. So if you make this large, if you consider a graph whose connectivity is large, then that forces the minimum degree to also be large. The converse, however, is not true. Conversely, large minimum degree does not ensure, same thing, ensure high connectivity. Not even high H connectivity. The author in the text writes this example. What sort of example shows that we can have high minimum degree in a graph whose connectivity as well as H connectivity is very low? And one natural example can be this. You continue taking as many vertices as you wish, make all of them adjacent to a single vertex, and also you draw like this. This vertex has oh no, we cannot do this, no? Because okay, large minimum degree does not ensure high connectivity. Okay, so okay, now this example does not work. I don't know what I was thinking about. So you have to find a graph which has large minimum degree but still it has low connectivity and low edge connectivity. Since if you have low edge connectivity, that will automatically make the connectivity also small. So we can think in terms of removing edges. Large minimum degree. Oh yes. Say you have the graph k in here, the complete graph on n vertices. Here also suppose you have k in. Okay. As a concrete example, you can take say k5 and k5. And join them like this. Okay. Then what is the minimum degree of this graph? Minimum degree is n minus 1. For example, in this case, these vertices have minimum degree which is 4. In this case, if you consider a vertex which is not one of these two vertices that have been joined, then the minimum degree of the graph will be equal to the degree of that vertex, and that will be n minus 1. By making n as large as you wish, you can make n minus 1 also correspondingly as large as you wish. However, because of the presence of this bridge, the edge connectivity of this graph, if you are calling this graph say G, is 1. So here edge connectivity is very small, but minimum degree can be made as large as we wish. And because edge connectivity must be greater than or equal to the connectivity, so the connectivity in this case is either 0 or 1. Connectivity is not 0 because the graph itself is connected. So connectivity is also equal to 1. In fact, you can see that if you delete either this vertex or this vertex, then the graph becomes disconnected. So that's why connectivity is 1. So this is a class of examples that shows that the converse is not true. Converse is not true means conversely this becoming large does not say anything about the other two quantities. Okay, now we next see the only other result from this section. This is the theorem one, 4, 3 due to someone named matter. Let k be a positive integer. Since the set of natural numbers for us contains 0, so this means k is a positive integer. Every graph G with the average degree of G greater than or equal to 4k has a k+1 connected subgraph H such that epsilon of H is greater than epsilon of G minus k. So if we have k is a positive integer, and if we have a graph G whose average degree is at least 4k, then it has a k+1 connected graph H whose epsilon value, which is also another sort of average, is greater than epsilon of G minus k. Let's first recall what this dg and epsilon g are. dg is the average degree in this sense. It's the sum of all the degrees of the vertices in G divided by the number of vertices. And epsilon of G by definition is the cardinality of the H set of G divided by the cardinality of the vertex set of G. These two things are of course the same, the order of G. And we have already seen that epsilon of G is 1/2 of the average degree of G. We have seen these things before. Okay, so let us now start the proof. So dg is the average degree and epsilon of G is this number of edges divided by number of vertices. We start by calling this epsilon of G something gamma, since d of G is greater than or equal to 4k and epsilon of G is 1/2 of d of G, we have gamma greater than or equal to 2k. We are now going to consider a class of subgraphs of G that is given by these properties. Now consider the subgraphs G prime of G such that there are two conditions. Order of G prime is greater than or equal to 2k and the number of edges of G prime is greater than gamma times the order of G prime minus k, and let us call these conditions collectively star. Now G may not have, the conditions look fairly complicated, so we don't know whether G has such subgraphs at all, G prime, but in fact G has at least one such subgraph. It is G itself. Note that G itself is a subgraph of G satisfying star. But how do we show that we can put G in place of these things? Suppose G does not satisfy this condition, that the order of G is less than 2k. Then we will arrive at a contradiction like this. 2k is if order of G is less than or equal to 2k, then 2k will be, you see, 2k is less than or equal to gamma. And gamma is what? Gamma is epsilon of G, and epsilon of G by definition is the number of edges in G divided by the number of vertices in G. Now the number of edges in G in any graph, say having n vertices, at most how many edges can be there? If all the vertices are adjacent, the number of edges is n choose 2, or in another language nc2. All possible, any two vertices are adjacent, so all possible edges are there. So this number is, the numerator is less than or equal to, n means number of vertices in G, choose 2, which is order of G, and this denominator of course is also the order of G, and this is what? Order of G times order of G minus 1 divided by 2 times order of G. So this becomes order of G minus 1 divided by 2. Okay. Okay. So now, because of our supposition, this thing will be less than 2k minus 1 divided by 2. So this implies 2k is less than 2k minus 1 divided by 2. So 4k is less than 2k minus 1, or 2k plus 1 is less than 0, which is not possible because k is positive. So our supposition is false. Supposition means this one, that is we must have greater than or equal to 2k. So G satisfies the first condition, and the second condition is also very easy to verify. Also, let us show that the second condition is equivalent to something which is obviously true. The number of edges in G is greater than gamma times the number of vertices in G minus k. This is equivalent to, if we divide on both sides of this inequality by the order of G, the number of vertices, then we get this. One minus k divided by this is what actually gamma is nothing but epsilon of G, and this is 1 minus k divided by this. Now this is nothing but epsilon of G itself. We will have to wrap this part. We will recall star when we need. And because epsilon of G is a positive real number, so since k is positive, we have 1 greater than 1 minus k divided by order of G. Thus, the equivalent inequality, these two inequalities are equivalent. Thus, this is also true. And hence G satisfies star. And so G satisfies star. Now we know that the class of such subgraphs of G prime is non-empty, so there will be a minimal such subgraph. Let that subgraph be H. Let H be a subgraph of G with the smallest possible order that satisfies star. Minimality of H will be used, and we are now going to show that H is in fact the required subgraph, which is k plus 1 connected and which satisfies those type of, the inequality that its epsilon value is greater than the epsilon value of G minus k. No graph G prime that satisfies star as in star has order equal to 2k. Because if that happens, then we have this. Since otherwise we would have because G prime satisfies star, so it will satisfy the second inequality, gamma times order of G prime minus k. So this will be equal to, so if you put 2k here, you will get 2k minus k is k, gamma k, and since gamma is greater than or equal to 2k, that is there in the beginning itself, so this will be greater than or equal to 2k square, and 2k square turns out to be strictly greater than 2k choose 2, which is the order of G prime choose 2. So the number of edges in G prime will in that case be greater than, strictly greater than the number of possible edges, which of course is not possible, which is false. So that's why any subgraph G prime of G that satisfies star must have order greater than, strictly greater than 2k, and H is such a subgraph, so order of H must also be strictly greater than 2k. The minimality of H thus implies that its minimum degree is strictly greater than gamma. But why? How actually? If delta H is less than or equal to gamma, then what goes wrong? If delta of H is less than or equal to gamma, then we can remove a vertex V belonging to this from H satisfying this. You see, if the minimum degree of H is less than or equal to gamma, that means H has some vertex whose degree is that minimum degree. So such a vertex can be chosen in H whose degree is less than or equal to gamma. But then what happens? Then what is the then H minus V is a proper subgraph of H such that two things will happen. What is the order of H minus V? Clearly, since we are removing one vertex, so this is order of H minus 1. But if you see, what we have proved here is that no graph G prime in star can have order equal to 2k. But according to the given inequalities in star, the first inequality that G prime satisfies is this. And we cannot have equality here, so strict inequality. In particular, since H also satisfies star, so we have this. Okay. And because these are integers, so this must be greater than or equal to 2k. Strict inequality implies this. So this is greater than or equal to 2k. And the other thing that will happen is this. What happens to the number of edges in this subgraph? Removal of V also removes the edges incident with V. That means this number will be the number of edges in our original H minus degree of V in H. Don't forget to mention that this degree is in H, okay, considering V as a vertex of H. Now, because of our this condition, this will be greater than or equal to this minus gamma. This is less than or equal to gamma, so when we multiply by minus 1, the inequality gets reversed and add the size, the so-called size of H, that is the number of edges in H, on both sides you get this. However, H itself satisfies the second inequality, namely this one from star, so its number of edges will be strictly greater than gamma times order of H minus k, and we have this minus gamma here. and this becomes equal to, if you take gamma common out, now note that this order of h minus 1 is nothing but order of h minus v. Minus k. So h minus v is a subgraph of G satisfying both the inequalities in star, that is, it satisfies star. Then h minus v is a proper subgraph of H such that, so h minus v satisfies star. But this contradicts the minimality of H, because H minus V has order 1 less than the order of H, but H has the smallest possible order, such a subgraph that satisfies star. And this is true when we consider this. This inequality allows us to find such a vertex V in H. So it cannot be true. So that's why we are having this. Okay, so delta H is greater than gamma. Now after doing all these things, this says that there is one vertex in H whose number of neighbors is greater than gamma. So the number of vertices in H in particular will also be greater than gamma. In fact, as a justification of this line, this is the justification, no? So you can keep this entire thing within brackets. It's not there in the text, but it is something that can be verified so easily, so the author has left it to us. So in particular, now the consequence of this inequality is this. This is greater than gamma. We need only greater than or equal to gamma, but we have strict inequality, fine. Now dividing the inequality, the other inequality that we have for H, that is coming from star, namely this one. Gamma times order of H minus gamma k. By order of H, we get epsilon of H equal to number of edges in H divided by number of vertices in H, that is greater than gamma minus gamma minus k. Gamma minus gamma k divided by order of, actually we get this. Now because of this inequality, what do we get from this inequality? If we divide both sides by order of H, we get 1 greater than gamma divided by order of h. So that means if we multiply both sides by k, is it making sense? And this in turn is equivalent to gamma minus gamma k divided by order of h greater than gamma minus k. This comes on this side, that goes on that side. So this quantity is greater than, yes, this quantity is greater than gamma minus k, and gamma is what? Epsilon of g minus. I don't really know how one comes up with this sort of arguments. Okay, so we have shown that h is a subgraph in G that satisfies the final inequality that we are claiming is true. Now the only thing that is left for us to show is that h is k plus 1 connected. So that is the next thing. Once we show that, then our proof is over. Now we show that h is k plus 1 connected. Suppose this is not true. So removal of k or fewer number of vertices disconnects h. I mean h has some k or fewer number of vertices whose removal disconnects h. The technical way of saying that is this: if not, then h has a proper separation disconnection. When we have disconnection after removing a set of vertices, then we will have a proper separation where none of these sets, these are sets of vertices whose union is V by the definition of a separation, as and whose intersection is the set that is being removed, and none of them is empty. No, that is not the definition of a proper separation. None of these sets is empty. U2 minus U1. A proper separation of order at most k, yes. So which is just another way of saying that there are at most k vertices that can be found in H whose removal disconnects H, and this separation means two sets of vertices whose union is the vertex set of H and whose intersection is that set whose removal disconnects H and its order is less than or equal to k. If this happens, then H is not k plus 1 connected, and conversely. Okay. Let H1 be the subgraph of H induced by U1 and H2 be the subgraph of H induced by U2. Since any vertex V belonging to U1 minus U2 has all its neighbors. How many neighbors? Degree of V neighbors. Neighbors in H, that is greater than or equal to the minimum degree of H, which in turn is greater than gamma, that we have already seen is true. This many neighbors from H in H1 has all its this many neighbors from H in H1. Naturally, because H1 is the induced subgraph of H induced by U1. So if you have any vertex in U1 minus U2, then all its neighbors that belong to that induced subgraph H1, that's not what I am trying to say. Any vertex here has all its neighbors from H in H1. Yes. Since that is the case, we have the order of H1 greater than or equal to gamma, which is greater than or equal to 2k. Is this clear? Since any vertex V in U1 minus U2 has all its neighbors, forget about this for a moment, has all its neighbors from H in H1. That is the definition of induced subgraph, right? If you consider two vertices in U1 which are originally adjacent in H, then in the induced subgraph also they will be adjacent. So that's why we have this statement, and that is why in H1 we have at least this many vertices, because this is the number of neighbors V has in H, and in the induced subgraph also they are neighbors, that is H1. So in H1 besides V, we have its neighbors already coming from H. So at least that many vertices are there in H1, and that number, since this is some degree of some vertex in H that is greater than or equal to the minimum degree of H, which itself is greater than gamma, we have shown that before. So order of H1 is at least this much, at least this many, and that is greater than gamma, and gamma itself is greater than or equal to 2k, so which is coming from the beginning itself. Similarly, order of H2 is also greater than or equal to 2k. as by the minimality of H, neither H1 nor H2 satisfies star. Why? Because this is a proper separation, so H1 and H2 are both proper subgraphs of H. So they are smaller than H, but H is the minimal subgraph in terms of order of G that satisfies star. So H1 and H2, none of them can satisfy star, but they are already satisfying, both of them are already satisfying the first inequality in star. So that means we are left with only one possibility, that none of them satisfies the second inequality. So that's why thus satisfies the second inequality means this is no longer greater than gamma times that means this is less than or equal to gamma times order of H1 minus K, and this is number of edges. Number of edges in H2 is also less than or equal to gamma times order of H2 minus K. But what is the number of edges in H? Clearly this is less, because these are induced subgraphs, less than or equal to the number of edges in H1 plus the number of edges in H2, and we can now use these two inequalities. So this will be less than or equal to gamma times order of H minus K plus gamma times order of H2 minus K, and that is equal to gamma times order of H1 plus order of H2 minus 2K. Now we can use these two inequalities, this one and this one. So now is that what we are using? No. That's not what we are using. We are going to use this. Here we have 2K. Note that we have one formula from set theory here. Or if one wants, one can write this more simply like this. This is nothing but U1, because H1 is the subgraph induced by U1. So the number of vertices in H1 is the same as the number of vertices in U1. In fact, U1 is the set of vertices in H1 plus U2 minus K is the order of the K is okay. K is not the order of the separation, but rather this is the order of the separation, which is at most K. But then are we not getting the opposite thing that we want? I don't understand this part. We are not able to. Oh yes, what am I thinking? So minus K is less than or equal to minus this. So if in place of one of these two minus K's we write this thing, that means we are writing more. So less than or equal to this minus K. Yeah, now it's okay. Gamma times. So this is our usual state theoretic formula, because this is a separation, so this is nothing but the order of H minus K, and this is a contradiction. What does it contradict? Which directly contradicts the second inequality from start that H satisfies. That is, the number of edges in H is strictly greater than gamma times the order of H minus K. So our supposition is wrong. Okay, we have not explicitly supposed anything. We are just saying that if H is not K plus 1 connected, then we end up with this absurdity. Thus, H must be K plus 1 connected, and this completes the proof. Okay, so that's all we have in this section. After this, in the next video, we will see trees, graphs which lack cycles, which are like this. These are all trees. Okay, so that we will see in the next video, and then we will continue like this. So that will be all in graph theory. If you want to say something about these things, you can of course write in the comment section below. So that's just it. So until next time, this is me, Lucifer, from a mathematical room. Have a nice night.